Welcome to The Explainer. Today, we're jumping into a real-life mathematical detective story. It's a puzzle that stumped some of the world's best minds for 88 years. Until now. We're talking about the deep, hidden rules that govern numbers and how one mathematician, Manjual Bhargava, finally cracked the code.
All right, so here's how we're going to break this all down. First, we'll get our heads around the central puzzle. Then we'll look at this amazing prediction from way back in 1936. After that, we'll see exactly how the proof works. It's super clever. And finally, we'll talk about why solving this is such a huge deal for the world of math.
Okay, so our story really kicks off in the world of polynomials. You know, those things from school, like x squared plus 3x minus 4. But we're not just solving for x here. We're asking a much deeper question about them.
So, let's say you could just reach into a bag and pull out a random polynomial. What would it look like? Well, there's this amazing idea called Hilbert's irreducibility theorem, and it basically says that almost 100% of the time you're going to get what mathematicians call a generic polynomial.
But here's the cool part. What about the ones that aren't generic? Well, it turns out there's this tiny, infinitesimal fraction of them that are incredibly special. They're not random at all. They're actually governed by these beautiful, hidden rules and internal symmetries. And the big challenge, the real mystery, is figuring out just how rare are they, really.
To actually measure these symmetries, mathematicians have this incredible tool called a Galois group. You can think of it like a secret decoder ring for a polynomial. It tells you all the possible ways you can shuffle its solutions, its roots, without actually breaking the fundamental rules that define it.
And this is where you see this huge difference. For a totally generic polynomial, its Galois group is what's called the symmetric group, Sn. That basically means maximum chaos. You can swap any root with any other root, no problem. But for those special polynomials, the Galois group is smaller. It only allows for very specific, structured shuffles. It's this hidden order that makes them special. So that leads us right back to the big question. Just how rare are they?
Well, that exact question, it takes us all the way back to 1936, to a mathematician who didn't just have a hunch. He made a really bold and surprisingly precise prediction.
Yep. van der Waerden didn't just say, hey, I think these are rare. He came up with an exact formula for how rare. He basically said, look, if you start counting all the polynomials where the numbers, the coefficients, are less than some big value h, the number of special ones you find will grow at a very specific, much slower rate. And this is the magic formula, O of h to the n-1. So what on earth does that mean? Okay, try to picture this. Imagine all the possible polynomials you can make are points inside a giant n-dimensional cube. Van der Waerden's idea was that the special ones aren't just scattered randomly throughout that whole cube. Nope, they all live on a single, super thin, flat surface, an n-1 dimensional slice, cutting through that bigger space. They're just fundamentally simpler than all the rest.
But proving this idea? Wow, that was a whole other story. It turned into a mathematical marathon that was passed down through generations. Van der Waerden himself could only get part of the way there. Then over the decades, you had brilliant mathematicians like Gallagher and Diepmann making huge leaps forward. But the full, complete proof, that remained just out of reach. Until this year, when Manjual Bhargava finally crossed the finish line.
So how do you do it? I mean, how do you solve a problem that stumped the best minds for almost a century? Well, Bhargava came up with this absolutely brilliant strategy, a classic divide and conquer.
Instead of trying to wrangle every single special polynomial at once, which was basically impossible, his proof elegantly shows that every single one has to fall into one of three neat, tidy categories. It's genius. By proving the conjecture for each little bucket, he proved it for everything, all at once.
And the proof is so clever because it sorts all these special polynomials based on a number called the discriminant, which is just a fancy way of measuring how the polynomial's roots are spaced out. So case 1 looks at polynomials with a big discriminant made up of lots of small prime factors. Case 2 looks at the ones where the discriminant itself is just small. And case 3 handles the rest, the ones with a big discriminant built from big prime numbers. By tackling each of these scenarios one by one, Bhargava showed that in every case the numbers worked out perfectly.
Okay, so an 88-year-old math problem finally gets solved. That's an incredible achievement for sure. But what does it mean beyond that? Why should we care? You know, in mathematics, proving something this fundamental is never just about getting the right answer. The real prize is often in the journey itself, all the new ideas, the new techniques you have to invent to get there. Solving this gives us a much sharper, clearer picture of the basic structure of numbers and even shapes.
And we're already seeing these amazing ripple effects. The proof shows that for polynomials that are even more special, with even more restricted symmetries, they're even rarer. It's like finding a single line drawn on that thin slice we talked about earlier. And it has consequences in geometry too. It proves that most of these complex shapes called hyperelliptic curves are actually, well, pretty simple. They almost never have extra symmetries. This work has basically given mathematicians a whole new, more powerful set of tools for counting all sorts of things.
Bhargava's proof is just this incredible testament to creativity and just sticking with it. It reminds us that even these problems that seem completely impossible, that have stood for generations, can totally fall if someone comes along with a new way of looking at them. It really makes you wonder, doesn't it? What other huge mathematical mountains are out there just waiting for the right person to finally draw the map to the top?